Hello all, welcome to my channel. I'm back with a new video. In this video, I will be discussing how to do Iceberg table maintenance. So let's get started. So first thing first, why uh, Iceberg tables degrade over time? This is one very important thing to understand. The biggest problem is the small file problems, uh, fragmented manifest, snapshot sprawl. So these are some certain things which are there to make it more understandable in a sense. Let's walk through what happens when we run certain commands. So when we run a normal create table, there is an manifest file, sorry, metadata file that gets created in the location where iceberg table is there. When we run an insert into table, and let's say we insert one record, even one single record that we have inserted, it will create these many files. So one is for the data file, which will have the parquet, which contains the data. Then we have a manifest, we have a manifest list, and then we have the metadata JSON, which is different than the older metadata JSON because the numbers change. So we will now, so let's say we run one create, one insert. And then let's say if we insert this multiple times, let's say we do insert one more time. So we will have how many? One metadata, which was earlier 1, 2, 3, 4. Then we will have 1, 2, 3, 5. And then we will have two sets of more the lower volume, these four files. So see, just if we keep on inserting it, let's say if we do 5, so we will have 25, more than 30 files. And let's say we have inserted 30 files and then we have inserted 5 times and then we run a delete. What will happen then? Again, it will create different metadata. It will create a delete file which will have a parquet which has a reference to the older file and a position delete marker saying that okay, this row has to be deleted. And then it will update the manifest, it will update the manifest list, and it will update the metadata as well. So you see, just by doing simple 3 or 4 commands that we run, we will have so many of data files or so many of files. And this is what we mean when I say these small file problems. Then the fragmented manifest. This is nothing but how many manifests are getting created, how many smaller data files are there. Then we have snapshots which are getting bigger and bigger because we have every change creates a new snapshot. So that's where the snapshot sprawl comes into picture. And the challenges with this is that it will keep on consuming the unnecessary memory of the system. It will inflate the table size even if the data volume is very static, slowing down the time travel and rollback operations because there will be too much of snapshots in there. For example, and the other things can be that the files which are being written is not following the right layout, right? It might happen that we have continuously inserted a lot of data, but we have inserted data over a time, and the grouping that we expected the data or the querying pattern of the data is not in the same way as the ingestion pattern. So the data that needs to be served should be in a different layout. The rows which are queries together should sit together. The rows which are seldomly are mutually exclusive, they should not reside in the same folder so that the number of scans or the amount of scan is reduced. So that happens. Then chances of partition imbalance is there because if let's say some partitions are having massive files, some are having very low amount of data, so the massive files will uh, create issue. And or it might happen that some partitions have very large number of small files. Again, there will be an overhead of doing a file listing and stuff like that. So the query planning becomes very difficult in overgrown partitions. So these are the re reasons why the iceberg tables degrade over time. So and what happens due to this degradation? Like the performance takes a hit. The queries will not run in that time. Even the writes will start to slow down because each time it has to do those many manifest updates and everything, so it slows down. Storage inefficiency, like we will have extra cost for the storage because we will be having too many smaller files. Metadata bloat, so metadata will become very bloaty, in a sense it will have too much of data to be covered. Operational overhead, because if we have too much of like when we run a compaction at on a very bloated table, it will take a longer time to combine those small files, and rewrite will also take time. Freshness will be reduced in a sense, if we have uh, if we are querying for the latest data, because it has to do the whole metadata parsing and before it reaches the data file, the responsiveness will be slow. So these are the challenges, and why the aspect tables degrade over time, what are their adverse effects. Now comes the part which we are interested in, is how do we fix this? How do we make the process or the table be always updated in a sense that it provides the expected uh, performance levels or expected SLA levels for certain things. So first thing that comes is compaction. This is just a mapping between what was the issue. So the first issue was small files. So to fix that, we run compaction. What compaction does, it creates a fixed size data file based on the number of smaller files that are present. For example, if we have 10 files, each having 100 records, then we can combine them to create one single file having 1000 records. And that technique is known as, I mean, to create the bin packing algorithm is used. And it what it does, it also, while compaction, it also merges the delete file with the data file that you saw we in the previous demo, that sorry, that slide. So where we had delete command creating a new delete file, so all those things gets merged as well during the part of the compaction. Again, what I am saying, the only the delete files are merged, not the delete files is not merged with the data files. So delete files itself themselves get merged, and we have other options of running. We can run the compaction with bin pack or sort or ZORDER. So there are three strategies to run compaction on. So a typical compaction will flow will be like scan the table to identify small files. So we divide the threshold that okay, what is constituted as a small file, then it reads that file and merges to form small files within a partition, and then write the new files with a defined size. Let's say whatever is the size that we have decided. Let's say if we decided it 128 MB, then it will write for 128 MB file size. And if we decided 512, it will create that. So the size we have to decide. For example, here we have set target file size as 1 GB, so it will write a data file which will be of 1 GB, and then it will create a new snapshot that references the new files and then drop the older snapshot. Optionally, this is optional because if we want to time travel, we can keep that as well. So this is how we can do that from Spark. So Spark has an option. Iceberg tools in Spark has an option of called option, not an option, as an API called actions. So in that actions, we can call action for table, provide the session and then the table name, and we say rewrite files. So rewrite data files. This is the API which is for compaction, and then we provide certain options like target file size, how many concurrent file groups should be rewriting, partial progress should be enabled or not, or rewrite the job order based on the bytes descending, or whatever is the job order that we can decide. So these are certain configuration that we can use to run the compaction job. And there are some other configurations as well, man, we can pass this configuration as an environment variable as well, this is max concurrent file group, it is the same one. Max file group size in byte, this is the same one. Partial progress enabled, this is the same one. So we can provide few things as an uh, environment variable as well while running the compactions. There are certain tips for running the compaction, is that we should decide the file size based on the engine's ideal scan size. The engine is which is consuming the iceberg table. So let's say example, if your table is being consumed by Spark, so you decide your partition size accordingly. If your engine is, let's say, is Trino or Presto, or let's say ClickHouse or Starrocks, so you decide based on that engine which is consuming that data, you should decide your partition size. The partition scope, we should not compact, this is one good thing, is we should not compact the whole table in one go. We should generally only compact based on the partitions which are changed in the last time, and we should run this compaction frequently. So once if we only touch Let's say if we want to find out which ones have been, let's say, created recently, we can add a filter and then run this compaction command. We can also tune the parallelism. For example, this max concurrent file group rewrites, it's how many parallel rewrites will be happening. So for example, instead of doing that, okay, if it first reads 10 file, then creates a group, it can create groups beforehand and then write them parallelly as well. But that will be happen within the partition itself. Avoid overlap, like overlap in a sense, overlap in the work, like it do not compact a file or a folder or a partition which is being used, which is being written by some other process. Uh, Also, compaction jobs should run on an isolated compute rather than in the same cluster where from where it is being read and write. So generally, this is the reason this is done is that it should not interfere with the query workload that is going on. So generally, the administration of the lake house should be done on a separate compute pool. And also data rewrite, because it is an expensive operation, we should do it in off hours so that no one is impacted while the data is getting rewritten or the jobs are not getting impacted. So there are few things like retry and checkpoint. We can also take care of that. Like for example, we should ensure that the compaction job runs fully. So if there is a failure based on the error code, we should retry again. And if the retries also are happening, we should be doing it in a fault tolerant manner. We should add a jitter or a back off before we retry again. So this is one. And when should you run? The frequency wise, the frequency should be frequent writes is equal, means let's say if our table is getting written more frequently, getting updated frequently, then we should run more frequent compactions. But if it is, let's say, uh, getting written once a day, then we can do a daily or a weekly compaction as well. Query behavior, if the queries touch recently ingested data, then we'll have to compact often. If let's say the queries do monthly reporting, then the newer data might not have to be compacted. The older data needs to be compacted first. So based on the query pattern, we can decide which table, which part of the table has to be compacted at what frequency. Table size, let's say we can do a table size check as well, like table stats or metadata from the Iceberg itself to find out which tables have larger data, and if they have a larger data, we should do more one. We should do one batch compaction, and then we should do the incremental compaction to keep that table in check. So yeah, and one thing it is that all the compaction history like bin pack, Z sort, or just or Z order or sort, they all reduce the data as scanned by the query engine. So hence they will reduce the processing cost as well. Now comes the second part, which is sorting, which is part of, we can think of a part of the compaction strategy itself. Why sorting is important is we can look at from this picture. So let's say we have an unsorted table. So we will have 0 to 9 in, let's say UID with 0 to 9 is in one particular data file, then we have 0 to 9 in another data file, 0 to 9 in another data file, because these tables are not sorted, like the values are not sorted. So what will happen, any record between this range 0 to 9 can fall in this, anyone can fall in this. So there is no proper order. But if we sort the data, then what will happen? 0 to 1 goes into this, 2 to 4 goes into this, or 5 to 9. If it is an even distribution, this is not even because it has two records, this has three records, and this has 5, 6, 9 records, and 6 is missing altogether. So yes, so if we have sorted data, what will happen? Let's say we are trying to find, in this case, we are trying to find UUID 1. So what will happen is that these two partitions will never be touched, because that it will find in the first place itself. It knows that, okay, what is the lower bound and what is the upper bound in a sorted fashion. So it will know, okay, 0 and 1. So 1 can only be here. It can't be in these things. So these things will never be scanned. So that's the power of the data sorting that helps in skipping the rows. So similar to what we had, we can add a table update sort order, and then give the sort name, sorting column name, and then order, like it should be descending, ascending, and then do the commit. So this is for the sorting. Uh, we can also do Z-order clustering, which is something similar to updates order. I mean, it's a same sort order API itself, but only thing it's it accepts extra flag that we can pass to the column saying that okay, Z-order based on these three columns rather than doing it for only for one column and ascending descending. This will help us in leveraging uh, query patterns which are generally used in the predicates of the column or group by column. So that helps with the reduction in scanning further. So now it comes the question of when we should be applying clustering versus when we should be applying Z ordering. I mean, when I sense not one versus other, it's what time like when ideally during the initial writes we should if the engine supports there only we should provide a sort. For example, in Spark before writing the data to the disk, we can say that okay sort this data. So that can happen. Uh, or we can rewrite the job as part of the compaction job with a sort order or in that way we can leverage this sorting and there are certain like techniques like which type of sort we should be using for which column. So let's say if we are filtering on one key column, then simple sort is fine based on that column. If we are filtering on ranges on a timestamp, then sort on time. If we are doing multi-column filtering, let's say multiple predicates are there in the where clause of the SQL statement, then we say Z order on those columns. And if joins is happening on a particular key, then we sort on the join key. And if it is in complex OLAP style filters where we don't know the whole pattern, but we do know the dominant columns that will be used across many OLAP queries, then we should do the sort order, Z order on that. So this was on the sorting part of the data. Then comes snapshot expiration. So why we do need snapshot expiration? So every update, delete, create, means every CRUD, like write, update, delete, insert in Iceberg does create a new snapshot. While it keeps an older snapshot. The reason for keeping the older snapshot is for time travel, as well as Iceberg follows snapshot isolation. So it does not update any existing snapshot. It will always create a new snapshot. So what happens if we have too many snapshots? So our snapshot sprawl will keep on growing, and we will see a increased cost, because if the snapshot is pointing to certain data set in older versions, it will still be there. Data will not be deleted. So that's where we have to expire the snapshots on a regular basis. And for that, there is an API called expire snapshots. And then we can say what, like this simply says that 7 days before older data will be deleted for this. So means only the last 7 days data will be kept and older data will be deleted. But it also said retain last two, means it will keep the last two snapshots no matter what. Like if the last snapshot was even before 7 days, it will not be deleted, because we are saying that okay, retain at least two. So that's the API to make the snapshot delete. Let's say this simply deletes older snapshot of 7 days, and it will also delete the orphan data which is present, which is not being referenced by any snapshots. So then that will reduce the cost as well. So again, how frequently we should be running this snapshot expression? We should run this snapshot expression every time we do a backfill. And for streaming workloads, we should do it with a high commit frequency, because in streaming use cases, generally the snapshots will keep on coming up fast. Anytime when we do a compaction, that because it creates a new manifest, the new manifest will create a new snapshot. So that time also we should be doing snapshot expression. Or let's say if there is an schema change, that time also we should be doing a snapshot expiration. And in general, we should always do on a schedule basis. Also, one thing to note is snapshot expiration is irreversible. The reason is because time travel capability will be lost, so we won't be able to go back to a point where we didn't wanted the system state to be in. So yes, that is one thing to note, that snapshot expiration is irreversible. Now rewriting the manifest, as we saw when we write any new data, there are new manifests created. So many manifest may reference the same file across snapshots, or some may contain only few files due to small writes, or their layout may be suboptimal for query planning. So for those reasons, we might want to rewrite or merge the manifests, and for that the API is rewrite manifest. Simply it does it. It will rewrite the manifest and create a new manifest and update the snapshot. That's it. And for example, manifest file we can query as well, that table name, and then if we say manifest, it will list the manifest. Similarly, we have other metadata API like table.files will list the files that are there, and this gives the manifest, and then we are calculating few things like how much data is there, or how much is the size of this manifest, average size, and all stuff like that. Removing orphan files. Orphan files are files which are not being referenced by any of the snapshots. They are sitting just as an orphan. Those will never contribute towards a query which is using the catalog. If someone queries directly on the file folder location, those files will contribute towards the result. So if we want to remove that, we can simply say delete orphan file API call, and that will delete those files. So to make it in one file, we have this script which is a summary table kind of. So expiring the snapshot, deleting the orphan files, rewriting the data files, rewriting the positional deletes files, and then rewriting the manifests. So these are the files, and whatever we have done in the Spark API, we can also do it in using the Iceberg tools using SQL approach. Like we can call SQL from the tool, and then let the system decide how to run it. And again, this is same like all those APIs are similar, like system.rewrite data files, rewrite data files, rewrite data files, rewrite data files, expire snapshot, remove orphan file. So yeah, these are the things that we can do it using SQL as well. Uh, Schedule maintenance, as we discussed earlier, also batch jobs we should compact on daily basis. Streaming jobs we should leverage Flink to do the Flink or whatever is the hourly rate that we want for the system or a streaming engine to do. We should leverage the streaming engine itself to do the incremental compaction as well. And in case of hybrid, we can monitor a metrics and then trigger the compaction based on certain thresholds that we can see. And so these are other, for example, there are certain metrics that we can enable on the table so that those metrics are captured in the Iceberg catalog itself. For example, if we want to know metrics for a column called user ID, session ID, event payload, and event type, we can decide like this, and then it will say truncate to 8 characters and just keep the values. So whatever metrics that comes out of these columns will be available in the in the table's metadata. Such a schedule for high volume streaming pipeline, we should do an hourly or event based compaction, and snapshot expressions would happen every 1 to 3 days. For daily batch ingestion jobs, we should do post batch, we should do a compaction, and snapshot expressions should happen for every week or every 2 weeks. Low latency analytics, we should do compaction on hourly basis and snapshot expression on 3 to 5 days. Regulatory or audited data for purposes where we want to keep the data for longer, we should do a weekly compaction, and then we should do a snapshot expression every 30 or 90 days based on the compliance rule that we are trying to follow. Then we have execution order. Generally, there is no hard and fast rule to write, but this will be the right order, I believe. So the first we rewrite the manifest, then we rewrite the data file, we rewrite the positional deletes, we expire the snapshots, and then we delete the orphan files. So that's how it should be, the order of the files, of the order of the operations to do the Iceberg table maintenance. Some of the best practices are only optimize the compact the affected partitions. So we can use leverage metadata to find out which partitions to compact, and while doing that, we can add an where clause to filter out only those partitions, and then run the compaction. We should do frequent and incremental maintenance rather than doing in one bulk. We should keep on maintaining the table at a regular frequency. For large tables, we can use Spark or any distributed computation parallelism to do the compaction in parallel and do leverage partial checkpoints and partial progress. This enables partial checkpoints and partial progress. What it does, it let's say it is doing a compaction on, let's say, 4 partitions, and for some reason, let's say the second partition fails, then it will not roll back the partitions which had already been compacted. We can restart from that particular point itself where it failed. So that will save us cost on retries. Also, retry only failed partitions. We should not be doing, when we retry, we should always retry on the partition which has failed. And also, every time that we retry, we should narrow down the scope for which the job is failing, and then first fix that and then redo the compaction for other parts. Also, for every compaction job or any expression or any job that, or any maintenance job that we run, we should try to do maintain its it maintains bookkeeping for that, and then we should have an audit table to regularly gather the data out of that maintenance jobs that we have. So this is it for this video. If you like this video, do share it, and this blog you can read as a reference. This will help you to understand how to do table maintenance. There are certain tools available. There is one called Apache MRO, which is a catalog for Iceberg. It has a UI as well, which can run the maintenance. There is another project called Nimtable, which is also doing the table maintenance. And there are a few others as well. Iceberg Compact RS is an Rust implementation of Iceberg catalog, and we can run those. We can run that to do the compaction and other table maintenance activities. So yes, that was it for this video. Thanks. Have a nice day.